Grazie.
Okay. Niente. Okay, so we start with this first slide that you saw already yesterday, where this is HL Tau. This is a very famous image now that was done in 2015 from ALMA. And you have here a disk that is one of these relatively old compared to the class, if you remember from yesterday, the class 0 and class 1. This is a slightly more evolved between class 1 and class 2 stages, but already shows these beautiful rings that most likely are carved by young planets. So we will see today some of the big issues of planet formation. Planet formation is one of these fields that is really hard to catch up because things are moving very, very fast. And there are lots of new results now, especially with ALMA. So it's, you know, I will urge you to basically, if you're interested in these, to look at some of the papers that I will show you and keep up with the literature, because every day there is something new. So I think my lecture will be already, say, probably slightly old because some of the things I put is, say, from, say, a few days ago, and I'm sure things will evolve very fast. Okay, so the first slide here I want to put is in fact to advertise a new review that from Karin Oberg and Ted Bergin that is available on the archive, where they actually give a broad view of the observations of protoplanetary disk. And also they talk about not just the physical, but especially actually the chemical processes. So here, for example, you can see the central young star, and then you have the disk with this shaded, say, blue and also pink, showing here, for example, that the density is decreasing toward the outer part of the disk, and the temperature also becomes cooler in the outer part, of course, because of the stellar irradiation, partially, as we will see. And also many things goes on. So there is some, say, turbulence, there is grain growth, evolution. Here you can see that you have, for example, settling, inward drift, and fragmentation when you have collisions with dust grains, and so on and so forth. A lot of chemistry, photochemistry, for example, if you are quite close to the atmosphere of the disk. And also, and this is very important, because the grains are basically covered by these thick icy mantles, if they get too close, say, to the young stellar objects, so the temperature is relatively large, their icy mantles sublimate, so we get what they're typically called these snow lines, and we will talk about those as well. So also the composition of the gas and dust will change across the disk, and of course this will make a important difference when we consider the composition of the future planets. So the outline today, we will talk a little bit about the growth of solid bodies and the main problems related to that, a mention to our solar system and what we know about its formation so far. Exoplanets, so a little bit about the observations, and then we will talk about their formation, because this lecture is mostly about planet formation. And then we will actually, for the formation, we will focus on the gravitational instabilities and the core accretion scenario, that are the two models that are currently say both valid and both wrong. Maybe both of them are true together, so there's still some struggle to understand which one is better. And then if there is some time, a little bit about the migration. So for the condensation and growth of solid bodies, here is just to show that when you start with these clouds, as from yesterday, dense cores, then you form your protoplanetary disk. And you see this is the end point of the protoplanetary disk. So you are left with planets, and these are the well-known planets to us. And so we have the terrestrial planets and the, say, giant planet in the outer part. As we will see, this is actually can be understood from the model of the solar system because of the presence of this water snow line that increases the mass of solids beyond this snow line. And so then you can get these larger planets, as we will see. So let's start then for how this condensation come about. This is actually a good question, I would say, because we still are trying to understand that there are lots of both simulations, and as you can see here, but also, of course, observations, because from the sky we have tons of these interplanetary dust particles, the IDPs, that can then be studied, and you can see that are a combination of kind of glassy silicate material stuck together, kind of not so, say, chemically bound together, but more like bound together by not so strong forces. And it seems like a scenario, at least for these IDP particles, that there had been some kind of gentle accretion of these particles. Now, remember that the interplanetary dust particles are leftovers from the passage of comets. And you know that comets are really icy bodies that come from the outer part of the solar system, which in fact are highly porous. So as I wrote here, the mechanical and chemical process related to grain agglomeration is very poorly understood. So we know that you can form this loosely packed fractal structure, and what is this force that is holding these things together? These are the van der Waals forces. So it's like a dipole-dipole or dipole-induced dipole forces among the molecules that form these structures. So if you have small grains, and you start in a sense with small grains from the interstellar medium, when you have your dense core, you have dust grains that have grain size distribution going from, say, 10 angstrom in size up to maybe 0.2, 0.3 micrometer, although some larger grains could also be present. So they are relatively small. In this regime, small grains are typically, say, quite strongly coupled with the gas. However, in case we are, say, staying within 1 centimeter, so solid particles smaller than up to 1 centimeter, the dust-gas coupling is described by this equation here, which is actually the drag force, or is called also the Epstein's drag. So this law is giving you this drag force that is equal to this A, which is the projected surface area of the body, rho g, of course, the gas density, the velocity of the body with respect to the gas. So you have to have some kind of relative velocity to have this drag, of course. And then CS is the mean thermal velocity of the gas that we saw it yesterday. It's like our sound speed that we were discussing yesterday. So this is the main equation that you want to use to understand this dust-gas coupling. And what happened actually when grain condense? So these dust grains, they feel, of course, this drag, but also they feel the gravitational attraction, say, from the star. And if the dust grain, for example, like in this figure, is a little bit above the mid-plane, what happens is that the vertical component of the stellar gravity pushes this dust grain toward the mid-plane. So the say understanding of this process, which is called sedimentation, is that with the time you have for the formation of a thin layer where the dust to gas mass ratio here is much larger than, say, the interstellar medium dust to gas ratio. And in this case, if you run simulations, you can, say, protoplanetary disk similar to the solar nebula, then you can see that this sedimentation can actually happen relatively quickly. So you have these solid bodies confined in a thin disk. There are lots of approximation here, of course, because we are considering relatively static type of disks, etc. But it's an important process that needs anyway to take into account if you want to model the planet formation. So sedimentation, this Epstein's drag, and then there is another important, say, interaction between solids and gas that actually it's a bit problematic, and this is what is causing a lot of trouble in the planet formation models of these, say, relatively well-behaved disks. So, of course, to make planets, you have to grow these particles from centimeter size to at least a kilometer size. I will tell you why you have to go to kilometer size. And this, of course, depends on the relative motion between the various particles, because if they all move at the same velocity, they will never basically encounter each other. So we just said that the motions of these centimeter size or smaller particles are coupled with the gas. But there is a difference between then the gas and the velocity and the larger particles. And let's see what is causing this difference. So if you can consider that particles that are larger, say, than the centimeter size, they are basically orbiting around the young star with a Keplerian velocity. The gas has its Keplerian velocity, but because of this term, which is a pressure term and comes from the equation of the hydrostatic equilibrium that we saw yesterday, the gas feels an effective acceleration or gravity that is different from the Keplerian acceleration. So basically this is the force of gravity that then you can go from here to the Keplerian velocity of the material that is orbiting the young star. As you see, there is the force term plus this term that is this hydrostatic equilibrium pressure gradient. Now, think that, and this was clear from the second slide I showed you, the pressure is decreasing going outward. So as this term here is actually negative if you move in the outer part. So basically you have a smaller GF compared to the Keplerian, if you just consider, say, the gravity. So as I wrote here, considering that the pressure is much more smaller than gravity, one finds that the gas rotates about, you see it's a small number, 0.5% slower than the Keplerian speed. I was thinking, in fact, to include this demonstration, but it takes a couple of slides, so I decided to avoid it because you can actually do it yourself just looking at this Weidenschilling paper in 1977. He was the first to actually warn about this problem of this difference in velocity between, say, the Keplerian speed and the actual speed of the gas. So just remember, and if you are interested, just read this paper. It's very clear, very nice paper, that the gas rotates slightly slower than the Keplerian speed because of this pressure gradient. So these larger particles that actually they move at the Keplerian speed, they feel this difference. So there is like a little headwind when you go to with your bicycle. So this headwind basically removes some of the angular momentum of these larger particles. And of course, this means that they will decrease the orbital size, so the size of the orbit, and they will basically just spiral inward toward the sun. You can calculate this based on the equations that I showed you in the previous slide. So if you have like a 1 meter size body at 1 astronomical unit, where our Earth is, this could take only 100 years before, you know, it moves onto the sun. So it's really a fast thing, and you really need to consider or make planets before, but you know, this is really too short. It's a big problem for this for the current say models of planet formation. So a consequence of this is that you know, there is on one side, you have this meter-sized planetesimal that can go toward the central region, while, for example, the smaller grains can be swept up basically by the larger bodies because they are following the gas. So with these headwinds, some of these bodies that are rotating, larger bodies that are orbiting around, can actually grow in size, but then they will spiral inward. So the material that survives then to form planets have to do it very quickly. And so you have to go from centimeter to kilometer size. And this is in fact problematic. So this sedimentation that I was talking to you before could be in fact a solution, because in fact in this case you could have, say, a material that is confined in this thin disk, and this is a dust-dominated disk, which is then just orbiting at the Keplerian velocity with not much influence from this headwind from the gas. So in this case, we could have, so people have been studying the case, for example, when you have a quiescent disk, so not much turbulence inside. So in this case, you could have this settling, relatively, say, easy to do. And then you can produce this planetesimal of the size, say, of about 1 kilometer, that you need this 1 kilometer to arrive at the limit above which you can start to grow gravitationally. If the disk is a bit more turbulent, of course, you can also do extra growth with two-body collisions. But the problem with this is that going from millimeter to kilometer in this small time scale is quite problematic. So why 1 kilometer size planetesimal? Well, in this case, for example, is the 1 kilometer, once you have 1 kilometer size body, the gravitational binding energy becomes comparable to this van der Waals binding energy that brings together these smaller pieces, as we have seen for the interplanetary dust particles. So this means that when the size is larger than 1 kilometer, basically gravity becomes more important, and you can have mutual gravitational perturbations and then, say, grow gravitationally attracting other bodies around, or for example, around the orbit. For our solar system, we know that, and this is based on the age of the oldest rocks that are, say, available to us, especially from the rocks that again fall from the sky. So we know that it was formed about 4.6 billion years ago. We also know, again, from rock-related and also simulations that models that have been done, that Mars most likely formed about, say, 13 million years after the formation of the sun, and then Earth took about other, say, 30 mega years to form. We also know about the Earth, that it's a very important event, and people are still currently studying. I actually see papers on this on a regular basis about the fact that the moon formation event that happened about 100 million years after the birth of the solar system. So you probably know this, the Earth was basically hit by a Mars-sized object, so it must have been quite how to say, terrifying experience. Of course, there was nobody there to be terrified yet, but this is what happened. So you had these bodies that collide, and then the energy of the collision basically made the Mars-sized object completely molten. And then you have also a lava magma ocean on the Earth, and then the production of a disk around the Earth that then will form the moon, which initially was very close to the Earth. And then you know that the moon is actually keep increasing its distance from the Earth by a little bit. But initially, when this moon-Earth system was formed, the system was, the two bodies were really close. So the rotation of the Earth was much faster. Like, the day was about 6 hours, and you can imagine you had huge tides. So it's fascinating from my point of view to think about, these early phases of the Earth, also because we know that life started very soon after basically the formation, after this impact system. So it's really fascinating. Anyway, so for the Jovian planets, what we know is that they, like Jupiter, Saturn, Uranus, and Neptune, must have formed very fast. And this is because you need the gas, and the gas is evaporated away after, say, 10, 20 mega years. From what we know from observation. So they must have formed within these 10 million years. Great. So for our solar system, this is the classical scenario of our, say, it's called like the solar nebula or minimum mass solar nebula scenario. So this was built by Hayashi in 1981. And he did a very simple, but at the end, you see, simple things at the end last for many years. Many people always refer to the minimum mass solar nebula also for, say, comparison with the current protoplanetary disk that we see around. So what he did, he said, okay, I don't know what was the initial structure of our solar nebula, but I know what is the distribution of our planets in our solar system. So what he did, he just took the mass of each planet, he increased the mass of this planet by the light elements like hydrogen, etc. This is especially important for the terrestrial planets where there is a little resemblance to the, say, solar composition. So he just increased the amount of mass based on the fact that he wanted to reach the solar composition. And then he spread the mass of each planet in an annulus center at the orbit of the planet, but then, with the size that goes, say, halfway between the planet itself and the next planet. So it's like grounding every planet and making say this augmentation of the mass, taking into account the extra hydrogen and helium and all these light elements. So what he found this surface density, so this is the mass surface density profile. So the disk in the minimal mass solar nebula goes like r to the minus 3.5 with this number here. This is normalized at 1 astronomical unit. So at 1 astronomical unit, you have 1,700 grams per square centimeter. This is the sigma gas. Then he also considered the sigma solids, so just focusing on the refractory material, and he found that he needs to increase at certain point by this factor F snow, the sigma of solids, and this is in fact is called the snow here because it is indeed the the factor changes at the snow line. So you have like a sigma solid here that is 7.1 grams per square centimeter, but if you are beyond the snow line, you have to change F to 4.2. And I can just see this, so visualizing this, I think it's easier to understand. So you have here your sigma, the radius, so this is your 1 astronomical unit, and this is the snow line. So this is the radius at which the ice, the water ice, becomes solid. So you can see that this is the gas, it's just r to the minus 3.5. But the solids, they have this discontinuity here because of the extra solids due to the ice. So you have rock, and here rock plus ice. And if you put our planets on top of them, you see that you have, of course, some dispersion. It's not exactly, he has a very, very simplistic parametric formula, but you have so each box here is a planet. The cross is the estimated rocky core. So you can see that the rocky core of the terrestrial planet basically is coincident with the planet total, say, mass, in this case, surface density. And here, on the other hand, for the giant planet, the rocky core is significantly smaller in surface density than the total mass, because in fact they have very rich, very big gaseous atmosphere. And we will see this later when I talk about the core accretion scenario. So in the solar system, and this is in a sense true in general, you have to consider this fact that it's also seen here, that if you move away from the central sun, in this case, you have definitely a composition difference at this stage, but it's not just water that freezes, but also many other volatiles can freeze out, including, for example, methane, ammonia, and we see these, in fact, also in the, say, giant planet, Uranus and Neptune. So they all have their own compositions that probably reflect these different condensation temperatures of these volatiles. Of course, if you are close to the sun, you will be left only with rocky material that have high condensation temperature, and this implies silicates, for example, or oxide, but mainly, yes, silicate, amorphous silicate material. And as you move outer, you will get more and more, say, ice on top of these silicates. To understand these, and for example, if you know the condensation temperature of volatiles, of the various volatiles, you can use the temperature, which is a simplified way to describe the temperature of a disk, just considering that the disk is heated by the central star. And actually, I didn't do the equations, but to get this equation, you just need to do to use the temperature expression, so thermal balance. So you have like equilibrium equation, so absorption of starlight must be equal to the emission of radiation. And if you do that, you see that the temperature is proportional to the luminosity, to the 1/5, so this is the luminosity of the central object, and divided by R2, so you have here -2 and then elevated to 1/5, so it's proportional to R to the minus 0.4. So it goes in the range of, say, about 1000 Kelvin in the inner radius. Of course, if you get even closer to the star, the dust sublimates, so you don't get any solid material. But if you move in the outer part, the temperature becomes as cold as, say, the dense regions. This is a plot showing the vapor pressure, so saturation vapor pressure for different materials. So now here the temperature increases toward this direction here. So it means that your star is in this direction here. So you see water is the first to freeze, but then you have ammonia, you have H2S. We have not talked about H2S, but it's similar to water. Instead of the oxygen has the sulfur. Then you have CO2, which is very important also for our planet component. And methane comes. So you expect to have a variation in composition as you move outwards in our solar system. This is a not to scale version of our solar system, where just to show the composition in general. So we start here with the Earth, asteroid belt, the giant planets, and then you have this region of the Kuiper belt and scattered disk that then is joined with this dashed line, because nobody really knows when the Oort cloud of comets begin at about, say, 1000 AU. And I always like to connect to what I said yesterday about the centrifugal radius, that if you put down the number and if you do this simple calculation of equating the centrifugal force with the gravitational force in a typical dense core that we see, you end up with this 1000 AU, which maybe is just a coincidence, but it's interesting. So I move on, unless you have questions, and I now want to talk about exoplanets. This is, I think, is probably the least up to date. I mean, I have tried my best, but I really, every day there is a new discovery almost, and it's really hard. So this is actually a picture that was taken some years ago already, but it's one of the rare examples where you can do in this case, I think it was done with the Keck telescope. So from Earth, you can do this impressive imaging. Of course, you need to have the perfect stellar system where you have, like a face-on stellar system where you see the central star. Actually, this is masked central star, and then you have the planets that orbit around. So with the multi-observations of this system, astronomers were able to find the orbital motion. So they found, in a sense, the first multi-planet system here, which is absolutely amazing because, it's always great when we see that it's not just our solar system that has several planets, but also there are other systems like ours. And now, as we will see, with Kepler and other instruments, we know of many other multi-planet systems. So before adventuring into this exoplanet, I would like to first define what a planet is, then review some of the main properties of exoplanet, and then we will go into the formation scenario. Here is a list of important papers and books, actually. So the Pater and Lissauer book of 2001 is, if you're interested in planetary science in general. Phil Armitage, this is a really important, very, very beautiful book if you like theory, and this goes into the physics of planet formation. And then there are several, even old, actually, I always like also these, although as I said, this is a field that is moving very fast. Also, these old reviews from protostars and planets 5 and 6 are really well done. They basically have all the seeds and all the main features that we see now with the Kepler mission, etc. They're already there. It's really unbelievable. Of course, they missed all the, say, lower mass planets, things like that. Then the chambers and the Pollack. This is the classic. This is the classic paper that shows the core accretion scenario, as I will see. The chambers, 2009, sorry, is the one where I took all these vapor pressure numbers in case you are interested in those things. So let's define a planet. So there is, of course, not really controversy, but you can understand that it's not really such a strict number. You know, we have some error bars here. So the definition that we are adopting here is that a planet is, say, a body that is not massive enough to undergo, say, any fusion, and in particular the deuterium fusion, that is the minimum, the first that comes up at, say, 1 million degrees when the central part reaches 1 million degrees. So it means that it has to have a mass less than 13 Jupiter masses. Above 13 Jupiter masses, you can actually get this deuterium burning. Doesn't mean that then it grows to hydrogen burning, but if in this regime where the deuterium can burn, you are in the brown dwarf regime, and this goes from 13 to 75 Jupiter masses. But they don't grow enough, yes, to have this fusion of hydrogen. The interesting thing about planets and brown dwarf is that they keep cooling down very slowly, but they keep cooling down. So there is no way, like for example, for the star, where you can have the mass luminosity relation, because in fact, you can see here from this diagram that at some point when the star, like the main sequence stars, start to fuse the hydrogen, then they stay stable for a long time, like our sun. And then you see that here the luminosity doesn't change for a long time. So then you have a nice mass luminosity relation. But for the brown dwarfs and planets, that's not possible. They just keep cooling down. So then I'm not going much into the observations, except for only this part here for the radial velocity, because again, this goes a little bit beyond on the planet formation lecture, but this is very important, and it's in fact, as you know, last year we had the Nobel Prize for that. So this is actually the first time that a planet was observed orbiting a main sequence star, so like our sun, say, this was done in 1995, and it was actually a 0.47 Jupiter mass, but you see here there's the sign I, where I is in the inclination of the orbit that is not known, but say less than Jupiter mass, orbiting with the period of 4.23 days. And this was discovered around this 51 Pegasi star. So you can see what Mayer and Kilos found in 1995. So you have here the radial velocity. So this is, I will explain actually in the next lecture, in the next slide, that this is the velocity that the star, the velocity change of the star while it is orbiting the common center of mass with the planet. So you see these very beautiful sinusoidal type of curves with all the dots here. And this is the radial velocity as a function of, say, phase, or also you can consider, say, the time so from one point to the next. So from here, you can actually get the period, and you can also get the kappa, the amplitude of the variation of the velocity, and the eccentricity. And I will show you in a minute how you do that. So since this basically discovery, we know now a lot of different type of stellar system, exoplanets. Many, especially the first detections, were of the masses much larger than Jupiter, because of course you can understand that if you have a massive planet orbiting a star, it will induce a much larger, say, radial velocity shift because of the larger mass at the larger pull, gravitational pull. We found, well, they found, I have not found anything here. So they found that the planets move on highly eccentric orbit, much higher eccentricities than our solar system that is close to zero. And they also found planets orbiting closer than 10 stellar radii, which is, you know, very small number. Consider that Mercury in our solar system is at 60 times the radius of our sun. Here we're talking 10 times the radius of the sun. And then planets with the resonant multi-planet system, very complex resonances. So, you know, these resonances is when you have, say, multiple so orbits. When you compare the orbits of various bodies, they go like with say integer numbers like 1 to 2, 1 to 4, and you know, some of these resonances actually increase the gravitational pull and can actually become unstable, and others instead are stable. So fortunately in our solar system so far everything has been stable, and we have in fact a very famous this is the 1 to 2 to 4 resonant for example for the Jupiter's moon of Ganymede, Europa and Io that have been yes measured since many years, and this is one of the stable things. So yes, this is to honor the two who actually, Mayer and Kilas, who did the discovery of this first planet. So yes, this is just explaining what I was saying before, so how it happens. So you just need to stare with your telescope. You have to have a good telescope and a good spectrometer here, you know, to be able to see these small shifts in velocities. And so you have the common, say, center of mass. This is the unseen planet, but what we see is this wobble. And then from here, you can arrive at the mass actually of the planet. And I will show you that in the next slide. So if you're curious, you know, in case you want to think of somebody who is trying to measure this radial velocity shift of our sun in a stellar system not too far away, that will be a little bit challenging because Jupiter is quite far actually from the sun. So in fact, the Jupiter's gravitational pull causes the sun to do this wobbling in a circle with the velocity of 12 meters per second. And this is really pushing the limits of the spectroscopic, say, capabilities of the current instrumentation, but I'm sure that things will improve and are probably getting already quite close to this. So this is just the few equation. In fact, I mean, if you work in exoplanet, your life is going to be very easy because at the end, it's okay, the observations are tough. The observations are tough and it's not easy to, you know, get probably the time that you need to the telescope to do all your orbits, etc. But once you have that, it's, you know, it's just Kepler's law. So it's at the end, you don't need any complicated physics. So you just need to remember the third law of Kepler, which can be written as this. Here you have the orbit, basically the semi-major axis. Yes, here is R, typically is written A, so I always confuse it. So it's the semi-major axis of the orbit. And then we have the period of the orbital period. So this is the third Kepler law with the stellar mass, our constant G and 4 pi squared. Then you have the Keplerian velocity. And you have the, to remember that you have conservation of momentum in just to solve this set of equations. So this product between the mass of the star and the velocity of the star must be the same as the product at the mass of the planet times the velocity of the planet. So from here, you observe, so you have all these equations, then you observe this K here, the amplitude of the shift. And this gives the velocity of the star times this inclination, because it's, as I said, this is something unfortunately not possible to measure unless you have transit observations. So in this, I'm not going into that, but if you have transit observations that you know that the planet, the orbit of the planet is actually the planet passing in front of the star, the inclination must be pretty close, say to be, say 90 degrees, and then you can do all your estimates. So here you have from all these equations and the observations, you can get this mass of the planet times sine I, so a limit of the planet, so minimum mass. Right, so with these radial velocity observations, this is in fact an old paper, so from 2007 in PP5, but you will see things have not changed much. If you put here the eccentricity as a function of this semi-major axis, so separation from the star, you see that, well, just to give you an idea, this is 1 AU, so this is where we are. You see that all these exoplanets span and actually the zero eccentricity of our Earth. So we are here, say. All these other planets are basically all over in this plane with masses that are some of them are even larger than Jupiter masses, and the size, in fact, of the symbol here is proportional to the mass. So there are many giant planets that actually are very close to their parent stars already here with periods less than 10 days. Can you imagine to put Jupiter inside the orbit of Mercury? And you know, that could be quite a thing to observe actually from here. And this is in fact was a big surprise. I mean, now we are all used already to that. You know? It's, oh, okay, I know that there are all these planets close to the, but if you think about it, when we started to work on this exoplanet, we only had our solar system as an example. And in our solar system, the big planets are very far. So Jupiter is at 5 astronomical units. And then you have all the other farther away. And that makes sense because you need these extra solids that are, for example, water ice, the most abundant, that needs to be solidified. And then, as you saw before, our giant planets are present beyond the snow line. So how can you have these big planets actually form close next to the star? So that is when, you know, question mark here, migration could be a case. So you have this giant planet form beyond the snow line and then migrated inward, or disk instability. So this is the gravitational instability scenario that was in fact started to build in because it could give an answer to this. So this is just a newer version of the picture that I showed you before. So you just see that there are more points, but they're still all very much spread around. And by the way, if you want to keep updated, you just go to exoplanet.org and you can actually make all kinds of plots as you wish. So these actually I didn't update because I was not able to reproduce these nice plots that I did in 2015 with the color here showing the planet mass. So you can see here, for example, this is a very massive planet, and I was not able to use the color. So I said, okay, and the new plot actually is very similar, so just more points. So I decided to leave this. But if you want to see the very like yesterday plot, you go to exoplanets.org and you can make all kind of correlation with the currently known exoplanet. So yes, let me go through these and then maybe after we can have a 10 minutes break. This is just to show how our view of exoplanets changed in the past years. So starting with the 1995, this is our planet, the first planet that was detected, that is where we were in 1995. Pretty lonely, I would say. Then, you know, 96 started to have, here you can also see, for example, yeah, the quality is not great, but so if it is yellow is transit Kepler, so of course there is no Kepler yet, so you don't see that. velocimetry or transit non-Kepler. So this is the radial velocity and this is the transit method. So you see that mainly at the beginning is mostly radial velocity, and then it started some transit, 98, 99. Here we had really the pioneer, say exoplanet people trying hard to improve the instrumentation, 2001, 2002, and so on and so forth. You see most is the RV, so radial velocity, 2006, 2007, you start to see, and this is, sorry, is the orbital period. I hope, yeah, you read that. So this is the radius of the planet relative to the Earth, and this is the orbital period in days. So you see the Earth is up here. Many of the objects are much higher masses. And initially we had this smaller orbit, but now with time, because there is more time to actually be able to look at these orbital periods also for longer orbit objects, more and more have been found at a higher orbital period. And then, yes, boom, in 2012, there was this increased number due to Kepler, who actually stared at many stars and found lots of planets via transit. The only problem with that is that I mean, this is amazing. This is really a great result. And I think it will take some time to, how to say, get significantly better statistics than this. However, I would say, you know, because the Kepler was staring at a part of our galaxy in a region that was, say, rich in star, which means actually the stars must be quite far away, just to have as many stars as possible. So that's the problem. I mean, we cannot follow up with more detailed observations these planets, unfortunately, because they're too far away. So this is the newest version of this plot, size relative to Earth as a function of the orbital period in days. So when you read now exoplanet papers, they already started to have their jargon, and their jargon comes from the location of these planets in this diagram. So you have the rocky planets, and this is easy because it's like our Earth. Rocky planets, the lava worlds, these are the ones that are very close to the star, but they're still small in size. So they're like big magma ocean worlds. Then there are the ocean and ice giants here. So you see here is 4 times the size of the Earth. Then you have the hot Jupiters, high mass and also close to the star, but also the cold gas giants. And these are like Jupiter and other big planets. And importantly, there is a frontier here. So this is the future. So future exploration, future instrumentation will actually try to look into this region here and see, for example, study planets that have, for example, terrestrial masses, but are orbiting the star probably at higher distances. So I don't know, if you want, we can stop here for a few minutes. Jan or Francesca,
yes.
Tell me, and then I continue.
Okay.
Okay, I don't know if there are some questions now.
Of course, yes, I'll be happy to.
Otherwise, we stop for a while.
Yes, so 10 minutes, what is the...
Yeah, would be okay.
Okay.
Are there any questions? Or students, or you prefer to do at the...
We can also do at the end. Yes.
Yeah, we can do at the end, everything. Okay, so stop for 10 minutes. Okay.
Thank you. See you soon.
You.
I stopped sharing just in case. Okay.